Hello Minecrafters and welcome back to another Restone video. Today we will discuss instruction set architecture or ISA for short. We will cover what it is, why it is important and how to make our own ISA for our Restone computer. So just sit back, relax, and let's get right into it. First, what is instruction set architecture? You can think of it as a contract between the software and the hardware of a computer. It defines how the software communicates with the hardware and what instructions the hardware can understand. For example, this is a C program that adds two numbers together. You and I can read this code and understand what it does, but the computer cannot. The computer can only understand binary or machine code. So we need to translate this C code into machine code so that the computer can understand. The ISA defines how this translation happens and what instructions the computer can execute. The reason ISA is important is that it allows software to be written in a way that is independent of the hardware. This means that the software can be written once and run on different hardware platforms as long as they support the same ISA. ISA also defines the CPU architecture. Different ISAs have different CPU architectures. For example, the x86 ISA has a different CPU architecture than an ARM ISA. This means that the software written for one ISA cannot run on a CPU that uses a different ISAs unless it is recompiled or emulated. Let's move on to the most important part of this video, making our very own ISA for our Restone computer. A simple ISA supports three main operator types, which are arithmetic and logic, data transfer, and control flow. For arithmetic and logic, we can have operations such as addition, subtraction, and some bitwise operations like NOR because it is a universal gate, left shift and right shift to move the bits around as well. For data transfer between the CPU and the memory, we can have operations such as load and store. Load will read data from the memory and store it inside the CPU memory, which is called registers. Store will write data from the CPU registers back to the memory. For control flow, we can have operations for branching, jumping, and calling functions. Branching allows us to make decisions in our program like if-else statements. Jumping allows us to go to a different part of the program, and calling functions allows us to reuse code in our program. We also have some other operations such as halt to stop the program and no operation or no op, which does nothing and is used for timing purposes. Now, is this a complete list of operations? Not really. We can always add more operations to our ISAs as we need them, but for this series, I think this is a good starting point for our Restone computer. Now that we have our list of operations, we need to define how to encode these operations into binary so that the computer can understand them. This is called instruction encoding. We can use a fixed length instruction format where each instruction is the same length in bits. An instruction can be divided into different fields such as the opcode field, which specify the operation to be performed, and the operands fields, which specify the data to be used in the operation. For this computer, I decided to use 16 bits to encode our instruction set. You can use more or less depending on many aspects such as how many instructions you want in your ISA, how many registers do you want, and how big is your memory space for instruction and data. In the last segment of this video, we listed out in total 16 operations. This means we need 4 bits to represent the opcode field since 2 to the power of 4 is 16. This leaves us with 12 bits for the operand fields. These operands can be register addresses inside the CPU, constant values that of our choosing, labels which are instruction line we want to jump to, addresses of functions in our code which tell the computer where the functions are, offset values to access data in the memory, or even nothing for halt instruction and no operation instruction. The splitting of these operands bits are all up to you. This part is very crucial if you want to make your own Restone computer. Because of that, I have made a Discord server dedicated to this series that you can join and ask me directly about how to design your very own ISA in more detail. Link to the Discord server is in the description. And that is instruction set architectural knowledge compressed down to a YouTube video. I had to take a 3 hours lecture on this this, so consider yourself lucky that you didn't have to spend that long to understand the basic of ISA. The rest of the series will be about trying to bring our ISA to life in the microprocessor layer that we discussed last episode. You will see exactly how we can implement each instruction in our ISA using Restone. So this will be the last non-Restone video of the series. At least I hope. I hope that you enjoy today's episode and also learn something from this as well. Thank you very much for watching, and I will see you all in the next Restone video. Have a nice day, everyone.